But for larger structures, like human-made reservoirs and dams, they can be large enough to move the Earth below. In 2008, 90,000 people were killed or missing and 5 million left homeless when a 7.9 magnitude quake ripped through Sichuan province in China. It is one of the deadliest quakes to ever hit that country. Just a few miles up on the Mingjiang River, the 512-foot-high Zipingpu Dam, which holds up to 1 billion tons of water, sustained large cracks. The dam is a concrete-faced, rock-filled dam, a style that's not built of solid concrete, but rather from boulders and sand topped off with concrete. This design is more susceptible to vibration. So when a quake hits, the boulders rattle, cracking the concrete shell. But critically, the dam held. If the dam had burst, the death toll could have been millions. Some scientists believe the dam was not only a victim of the quake, but that the dam itself helped trigger the quake in the first place.
The data we analyzed have shown that as soon as the water level increased in the reservoir, the seismic activity beneath it was increasing.
Here's how it works. As millions of tons of water fill up behind a dam, it can exert enormous additional pressure on the rocks below, the equivalent in mass of 3,000 Empire State Buildings combined. If a fault beneath cuts the right way, all that weight can sometimes stabilize the fault, pressing it together to prevent movement. But if a fault cuts the wrong way, all that pressure can have the opposite effect, causing a fault to slip. And the water's weight is not the only danger from human-made reservoirs. If water finds its way down into a fault, the results can be deadly. As human-made reservoirs are filled, hazards mount. Water at the bottom is forced down into crevices below the reservoir. Then that water creates additional pressure between the rocks called pore pressure. Pore pressure works quickly at any scale.
This box of dirt is dry, or the background condition of the earth, and I'm going to build a reservoir on top of it. This is a reservoir that's perforated at the bottom, and that also simulates the natural surface at the bottom of a reservoir. And I'm going to impound the reservoir now.
Filling a reservoir is called impoundment.
And so at the beginning, the water depth is pretty large, it's the largest, and you can see water drips down reasonably quickly. That's because the pressure in the reservoir is relatively large. The water now is percolating through the rocks, and it reduces the strength of the rock. If the rock is pretty strong at the beginning of the background condition, the water sifts through, makes it weaker. This is a small experiment, shows very quickly in a few minutes, but in real life, so the critical period would be the first few years after the impoundment of the reservoir.
The deadly quake in China's Sichuan province occurred just a few years after the rapid initial impoundment of the Zipingpu Reservoir, a reservoir that sits between two major faults. At the U.S. Geological Survey in California, scientists investigate the threat of reservoir-induced quakes.
If water can travel down through the fracture networks or through the pores in the rock and have direct access to the fault surface, then by raising the level of water in a dam, you raise the pore pressure on the fault and it can suddenly slip. Bingo.
David Lochner can't directly observe how water affects a fault miles below the Earth's crust. So he does the next best thing. He brings the fault into his lab.
This is a laboratory version of a fault. And if we want to study how faults behave, it may seem a little surprising, but the processes that go on this small handheld fault are very similar to what goes on in large crustal faults in the Earth. So in this sample, for example, we have a hole drilled in that we can inject water onto the fault surface. So see how water can affect the timing of earthquakes.
First, he secures the sandstone fault inside a cylinder.
A couple of clamps.
Next, he places the cylinder inside a pressure chamber, designed to reach pressures equivalent to those miles below Earth's surface.
There's a hydraulic ram that is in the bottom of this machine that'll push on the bottom of this piston and cause the sliding on the fault surface. Okay. Now I'm going to lower the shielding. This is all at high pressure, and we want to have some protection in case something goes wrong. Okay, ready to go.
Once secure, he cranks up the pressure gradually. At first without water, to see how the fault behaves. The fault holds, enduring pressure exerted nearly 2 miles below Earth's surface. Next, he adds water to the fault. Now, things change rapidly. The red line indicates increasing pore pressure.
That was it.
A reservoir-induced earthquake.
Water is a substance that, as you pressurize it, it'll obviously flow, and when it gets onto a fault surface, it actually can lubricate the fault and relieve the pressure that clamps the fault together.
And the faults beneath China's Zipingpu Reservoir have another potential weakness: a deadly orientation. All that water sits between two faults 10 miles below. They also run parallel to the reservoir along its length. This means the faults have the greatest exposure to the water and its weight.
If the reservoir was perpendicular to this fault, a much smaller area would be stressed, and maybe the earthquake wouldn't be that big.
In the U.S., the 727-foot-high Hoover Dam on the Nevada-Arizona border is the largest concrete dam in the country. The reservoir behind it is Lake Mead, the largest human-made lake in North America.
After the lake was impounded, a few years after that, there were reported seismic activities going on.
Since the lake reached its peak of 475 feet in 1939, the amount of seismicity has fluctuated based on water level. The reservoir induced hundreds of quakes where none had been before. None of those have been particularly damaging. The largest was only about magnitude 5. But could Hoover fail? It's not likely, since it's designed to withstand a 6.7 magnitude trembler. Still, reservoirs can trigger earthquakes. And if large dams like Zipingpu can cause such catastrophes, what might become of the largest hydroelectric plant in the world? China's Three Gorges Dam. When complete, it will store over 5 trillion gallons of water. It sits near 2 active fault lines and above 15 million people. It's built to withstand earthquakes up to 7.0 on the Richter scale. Good thing, since scientists expect earthquakes up to 5.5. But for Three Gorges, the danger of seismic activity may not only come from below, but also from above, in the form of landslides. When the reservoir fills, it creeps up the sides of the mountain valley, where the soil isn't accustomed to holding so much water. And if the rock layers beneath run parallel to the reservoir, they're more susceptible to sliding due to gravity. Even more so if one of the layers is clay, since clay gets slippery when wet. Unleashing so much earth at once forces a large tidal wave against the dam, and sometimes over the top. In 1963, that very phenomenon occurs at Vajont Dam in the Italian Alps. 13 billion gallons of water rushes through 7 towns, claiming 2,000 people asleep in their beds. It washes away everything in its path, leaving only mud in its wake.